to go.
Okay, cool. So hi everyone, welcome back. And yeah, so it would be nice if you can submit those open problems. I have one already from Aditya, and I'll be suggesting some as well. So depending on how many problems we have, we'll see if we want to keep the Friday session or not. We'll see. We'll figure that out later. Okay, so let's start with the topic. And today we get back to Ramsey theory, or at least the main problem that we have been talking about, which will help us in determining Ramsey numbers, in determining the off-diagonal Ramsey numbers. So we are going to use all the theory that we have developed in the last two lectures on polar spaces and now apply it to some nice combinatorial problem. Okay, so here's a reminder what the problem is. We want to construct clique-free graphs, so KS-free. S is a constant here, which are ND lambda graphs. So these are d-regular graphs on n vertices such that the second largest eigenvalue in absolute terms is at most lambda. So lambda I is less than equal to lambda for all I greater than 1, assuming lambda 1 is the maximum eigenvalue, which is d. We want optimally pseudorandom graphs, which is captured by this condition that our lambda is as small as possible. And we know that it can be at most, it has to be at least square root of d. So we ensure that it's at most some constant times square root of d. Moreover, we want the graph to be as dense as possible. So we want d to be as large as possible. And here we will have basically n going to infinity. So all this d and lambda, they'll be functions of n, and n will go to infinity when we are talking about these asymptotics here. And the way we capture this density to be as large as possible is we write it as this function, n to the 1 minus 1 over some f of s. And we want f of s to be as large as possible. And note that if f of s is large, then this thing is small, so the whole thing is large, right? Just to be clear on these things. And in the last exercise, we showed that f of s can't be bigger than 2s minus 3. And I mentioned this in the lecture as well. So ideally, we would want to construct something with f of s equal to 2s minus 3. And the motivation that we went for in these lectures was determining the off-diagonal Ramsey numbers. So we showed that this result of Mubai and Vastrate from 2 years back, which says if you can give such a family, such a construction, then you get the following lower bound on the Ramsey number R of s comma t. Here, the main thing to note is that the exponent of t is f of s plus 1 divided by 2. So if f of s was 2s minus 3, then this will be the correct exponent, correct power of t because of the matching upper bound. So that's the goal. But of course, we are far away from reaching that goal. In fact, the only value for which we know that f of s can be 2s minus 3 is f of 3 equal to 3, which was originally proved by Noga Alon in, I think, 1994. And then the question is, what about larger s? Right, that's the main problem that we want to focus on. And even though our motivation is Ramsey numbers, this problem actually predates the work of Mubai and Vastrate. This, in fact, this has been considered as one of the central open problems in the theory of pseudorandom graphs. So this has been stated by many authors in different contexts. And I believe some of the motivations are as follows. Well, firstly, it all goes back to the paper of Alon. So when he constructed these graphs, these triangle-free graphs, which are optimally pseudorandom and as dense as possible, and just in case you are a bit confused, we saw a construction by Koperty, right? We saw Koperty's graph. So Alon showed that these graphs can be used to solve some nice problems in both coding theory and discrete geometry. In fact, this construction was not just motivated by the Ramsey number by having an explicit construction for Ramsey numbers, but also by some other problems. And I believe whenever you have such a nice structure, such a nice graph, you would expect some more applications, some wider applications, especially for nice pseudorandom graphs. So we do expect that these graphs could be useful in many different contexts. But since then, since this construction and since the theory of pseudorandom graphs developed further, it was natural for people to ask that, okay, so Alon's graph is for triangle free, what happens for clique free graphs, right? What's the maximum density possible? And one interesting remark that I should make here is that, uh, so this n to the minus one third. So d over n equal to n to the minus one third, well, some constant times that, whatever, uh, for the n d lambda graphs, and lambda equal to, let's say, square root of d, something like that. So this is sort of a threshold, right? This is a threshold at which you start seeing triangles. So below this value, we have this graph which says there are no triangles, and we have all this optimal pseudorandom property. But as soon as you get above this threshold, you must have a triangle in the graph. And this is a common sort of a problem studied in random graphs in G of n comma p, which is the Alder-Shreni graph model. So these sort of thresholds that what should p be as a function of n, after which you start seeing some structure in your graph. In this case, just triangles. And I should mention that for the random graph, the threshold is something like 1 over n. So for the pseudo-random, hopefully it's correct. If it's wrong, then let me know. But there's a stark difference between these two functions, right? So for the pseudo-random graphs, you have a much different threshold. And something even more interesting happens at this threshold in pseudo-random graphs, which is that if you go above this density, then you don't just see triangles, you actually see triangle factors in your graph. You see a partition of all the vertices into triangles. And this is, in fact, the fact that this is the right threshold is a very recent result of Patrick Morris, who I believe is in the audience here. So congratulations, Patrick, for proving that. This was after a buildup of many years where people kept improving the threshold, and recently the correct threshold was proved. And then when you have triangle factors, you want to see clique factors also. So it's sort of a natural generalization. So this problem appeared independent of the Ramsey theory connection is all I want to say. And now we can move on to actually saying something about this problem. Well, as I said, we are far away from the conjectured bound, let's say. I think that's the conjecture that this should be true. But uh, let's see what's the best construction that we can actually achieve. And in fact, so let me erase this stuff. The best known construction is by Alon and Gribelovich from 1997, which says f of s equal to s minus 2. So there's a construction with this function. And of course, it only improves the triangle free construction when s is greater than 5, right? For s less than equal to 5, you can just take Alon's graph originally. You get the same thing. You get something better, in fact, for s equal to 4. Okay, so I will start with this construction, sort of describe the geometry behind it instead of just giving you the construction that they gave in their paper. And then we will improve that. And in fact, we'll use very similar ideas to improve this by 1. So this is by me, Ferdinand, and Valentina. Pepe, like 2020, basically. Yeah, 2019, in fact. But Yeah, so that's our final aim for this lecture. We want to get to that construction, which right now is the best possible, best known construction for this problem. And I really hope after this course that construction can be improved. Okay. So let's just jump straight in. Yeah, maybe I can go a bit slow. So if you have any questions about this, about the problem and what's the best thing known, just let me know. Because now we'll jump straight into the constructions. Any problem, any questions or anything, remarks? Okay. Yeah, I guess not. Cool.
Or
So
is it
you all want to
because
say?
why fs is at most 2s minus 3?
Sorry?
Why is fs at most 2s minus 3?
So you can show using basically the expander mixing lemma that if you have higher density, so if you have, there exists a constant such that if d is at least that constant, if d is at least that constant times n to the 1 minus 1 over 2s minus 3, and your graph is nd lambda with lambda equal to square root d, you can show using the expander mixing lemma essentially that there must exist a clique of size s. So I didn't do a proof of that. It was in the exercise, but I can probably post a solution of that exercise so that you have an idea. But right now, because we know this result, you can see that this is the threshold because of the upper bound on the Ramsey number. Right? The best known upper bound on Ramsey number by, I think, Aitai, Komlosh, and Semeredi, if I remember. Yeah, that has this function. The best known upper bound is t to the s minus 1, as in that's the best known upper bound. So f of s can't be more than 2s minus 3 because that will break the bound on Ramsey number. But that's a very indirect and difficult way of seeing it. You can just directly prove this as well.
Thank you.
Yeah. Any other questions or remarks? Okay, so I guess we can now begin our constructions. And this right here is in fact the main idea, and I believe the only idea we have had so far in the past 25 years or so to actually construct these graphs. I don't know any other idea for for these constructions, and that's the basic linear algebraic sort of idea. It says if you have a graph where the cliques of the graphs somehow correspond to linearly independent vectors in some vector space of dimension, let's say some function of s, then you can't have any cliques larger than the dimension of the vector space. So somehow construct a graph where cliques corresponds to a bunch of linearly independent vectors. And that's the original idea of Alon and Gribelovich. And that, yeah, I really don't know any other idea which has worked for any of these, except for s equal to 3. S equal to 3, we know, of course, other things, the general constructions. So let's explore that idea. And it might look like I'll make things a bit complicated, but hopefully they'll pay off in the end. So here is a construction using that idea, which is basically the Alon-Gribelovich construction. Okay, so let's start with an odd prime power q and let s be an even integer. Okay, so for now, our construction will only work when s is even. It will be fixed later, so don't worry. But for now, we will need this condition, and you'll see why. Okay, and now let Q be any non-degenerate quadratic form in the s-dimensional vector space. So just to be clear, we are working over the projective space of dimension s minus 1. Okay. And now when you have a quadratic form, you have a corresponding symmetric bilinear form, which is, okay, intuitively the dot product that you are all familiar with in the real geometry. And it's just given by the following. Okay, and now our vertices are all the points in the projective space. So every point in the projective space, which does not lie in this quadric. So where q of x is non-zero, and the edges are defined by orthogonality. So two vertices are adjacent if their, let's say, dot product or beta of x comma y is 0. Okay, so let's draw this. Yeah. You have this quadric Q, which is a subset of the projective space over FQ. And when we were looking at polar spaces, the graphs that we were looking at, okay, does the vertex have another name? Are they? Yeah, exactly. So these are the non-isotropic or non-singular points. Okay. So this is indeed the non-singular points. And in fact, when we were looking at quadratic forms and quadrics in the previous two lectures, the graph that we were interested in were the collinearity graphs of the polar space. And that is just taking points inside the quadric. So taking the singular points with respect to quadrics and defining collinearity as, defining adjacency as x being collinear to y, which is if and only if x is in y perp, which is the same thing as beta of x comma y equal to 0. So we already had a graph that looked like this, but earlier we were focusing on points inside the quadric. And now I want to define the same adjacencies, but for points outside the quadric in the projective space. And that's it. That's our graph. That's our first construction. And let's see why it has the properties that we want. First claim, this graph is free of any cliques of size s plus 1. So s is even, which we will use in the next claim. Right now, this is in fact true for all s. So let me remark, this is for all s. Okay, and here is the proof, which I think all of you would recognize from your basic linear algebra course. The proof is just one of the first few things you see in linear algebra. Okay, here's how it goes. Say U1, UK is a clique. Then from the adjacencies, we know that beta of ui comma uj is equal to 0 for all I not equal to j. Moreover, beta of ui is non-zero. So I claim that this implies that these vectors are linearly independent. Okay, so these are points of the projective space. They correspond to the one-dimensional subspaces. Just pick any vector in that one-dimensional subspace. Say this is a representative of the projective point. And now this implies that they are linearly independent because, say, the following was true. Then you just you just apply beta on both sides with various ui's. So then beta of this thing with, let's say, uj is equal to aj times beta of uj comma, and this thing is not equal to this thing is not equal to 0, right? But this thing is 0, so it must be that you have ai equal to 0 or aj equal to 0, right? This is the standard proof of the fact that if you have a bunch of pairwise orthogonal vectors in the real space, then they must be linearly independent. So this implies k is less than equal to the dimension, which was s. Okay, really simple proof, really basic idea that we have all seen. But we do need the following condition, right? We do need this. So in the real space, when you're doing this proof, you don't add that condition for the regular dot product because, well, no non-zero vector is orthogonal to itself in the real space. But now we are working over finite fields. That can happen. It does happen, in fact, for every point inside the quadric. So we remove all the points of the quadric, and then we can ensure that this argument works. So it's the same argument, we're just making it work over the finite field. Cool, so that's easy. So we have ks plus 1 freeness. Now, why is this graph nd lambda, right? That's the main thing that we want. So here's my next claim. And yeah, this will require some more effort. Okay, so I claim that this graph G is an nd lambda graph where n is roughly q to the s minus 1. So which is essentially the whole projective space, right? The number of points in the projective space is of the same order. It's also q to the s minus 1. So essentially in this picture, we haven't removed, if this is my projective space somehow, I haven't removed like a big chunk. I have removed a small order thing from the projective space. Okay. And now the second thing I claim is that it's a d-regular graph where d is exactly equal to q to the s minus 2. And for this, we need s even. So this is where we will use s as even. Okay. And finally, I claim that lambda is q to the s minus 2 over 2, which is square root of d. So you can check that here, this d is n to the 1 minus 1 over s minus 1. So this will imply f of s plus 1 equal to s minus 1, which implies f of s equal to s minus 2. All right, that's what we want to prove. And this is the result of Alon Gribelovich, basically. So let's try to prove that. Proof. Okay, firstly, the number of points, the number of vertices. Well, n is exactly equal to the number of points in the projective plane, projective space, minus the number of points in the quadric. And now if you go back to the lecture on polar spaces, we know that no matter what the quadric, the non-degenerate quadric is, it could be the hyperbolic one or the elliptic one, it still has basically these many points. Q to the s minus 2. It's a hypersurface, one dimension lower, right? And so this thing is, yeah, this thing is that. And this implies that Qn is essentially the whole space. Cool. So that was easy. What about D? And for that, we will use some of our theory from the polar spaces stuff. So again, going back to the picture, we have Q, which is the quadric. We have a non-singular point, which is a vertex of our graph, X. And we want to see how many points lie in X perp, right? Which are the orthogonals of X. So X perp is equal to all those y for which beta x comma y is 0 is a hyperplane to and it looks as follows. We have, this is our x perp, right? The point x is not contained in x perp because it's a non-singular point, right? That's why I drew it like this. Now, what we want to find out is how many points there are in x perp which are non-singular. So we want to find out the size here, right? We don't want to look at the intersection with Q. that is the neighborhood of every vertex. Is that clear? Right? That's what we are looking for. And we want to say what exactly the size is there. So now I just write a fact, which is sort of easy to believe, but not so easy to prove. So I'll actually skip the proof. X perp intersection Q is a non-degenerate quadric. So when you take a hyperplane intersection of this non-degenerate quadric, and that hyperplane is defined as the perp of a non-singular point, in this particular case, you basically get another non-degenerate quadric. This does not happen for all hyperplane sections. Right? It's only for these sort of hyperplanes. And because S is even, this implies that X perp intersection Q is a parabolic quadric in PG S minus 2, Q, right? If S is even, then S minus 2 is even. And in even dimensional projective spaces, there is only one kind of quadric, one kind of non-degenerate quadric, the parabolic ones. For odd dimensions, we have the hyperbolic and elliptic, but here we only have one kind. In fact, that's the reason why it's a regular graph. If we were working with odd dimensions, then this won't be a regular graph. We will have two different degrees, depending on what the intersection is. But right now, because X perp is an even dimensional projective space, this intersection is the same. It has to be a parabolic quadric. So it's the same sized intersection. So this is where we use S even. This is important. Okay, and now, well, we know how many points. So we know that this thingy here, this intersection, sorry, we know that this intersection is a parabolic quadric inside this projective space. So we know how many points we have to remove to get the value of D. So this shows that D is in fact equal to Q to the S minus 2 plus, yeah, I can write it in a different way to make things clear. Over Q minus 1, this is the number of points, minus the number of points in any parabolic quadric, which is Q to the rank, which is this, minus 1, Q to the S minus 2 over 2 plus 1 divided by Q minus 1. This follows from the previous lectures where we actually computed the number of points on any non-degenerate quadric. So this turns out to be exactly equal to Q to the S minus 2. If you just simplify things, right? This becomes Q to the S minus 2 minus 1 when you multiply these two things, and then when you subtract, yeah, that's the factor you get. Is it clear? Is that clear what the argument is so far? Any questions so far? I don't hear anything, so I'm assuming you're all sort of following it. Yeah, we're really using the theory that we developed in the last two lectures here. Okay, so we know the degree, which is Q to the S minus 2. So this is done. This is done. How do we actually compute the eigenvalues or estimate the eigenvalues? And that turns out to be slightly tricky. So this will take some time. Now, remember when we were looking at the same graph, but our vertices were the singular points of the quadric, then we had a strongly regular graph. And so when we have a strongly regular graph, it's straightforward to compute the eigenvalues. But now we don't have that. Now we are looking at non-singular points and the orthogonality graph on non-singular. So now we don't know if it's strongly regular or not. And in fact, it won't be strongly regular. So we can't use all of that. But we can still say something interesting about the adjacency matrix of the graph. So now we will prove the following claim, that lambda is q to the s minus 2 over 2, which is exactly, in fact, square root of d. So now let's try to prove this claim. And for that, let's look at the following graph, which actually contains our graph. So let A be the adjacency matrix of the same graph, orthogonality graph on all points of the space. So instead of, so here's the picture again. We define this graph on the non-singular point. So here, now I'm saying just look at the graph when you take this as your vertex set. Let's look at the same orthogonality graph, but now we look at all the projective points. What happens then? What does this A look like? And you suddenly notice that this is not really a simple graph, because all the singular points will be adjacent to themselves, right? Because every singular point is orthogonal to itself. So this graph will have loops. So in this adjacency matrix, we will have 1, 1, 1, and then dot, 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 1, and then 0, 0. We will have these many entries where the diagonal is all 1. Is that clear? Okay. And our graph sits inside the, so our graph has a vertex set which lies here. So in our graph, there are no loops. No vertex is adjacent to itself, so there are no diagonal entries equal to 1. So the adjacency matrix of our graph, the graph that we are interested in, will be a submatrix of this A. And so there is this very classical result, which I will write down soon, called Cauchy's interlacing theorem, which says that if you can find out the eigenvalues of this matrix, then any principal submatrix has eigenvalues which sort of interlace the eigenvalues of A. I will write down the precise formulation soon. So somehow, if you can compute the eigenvalues of this, then you have some hope of actually estimating the eigenvalues of the graph that we are interested in. So that's the basic idea. And the reason why we came up with this matrix is because this A is really easy to handle. Okay, so let me write down the following and ask you what exactly does this matrix look like? So this is a question for all of you. Can you tell me what exactly is A squared? So what are the entries of A squared? This was my matrix A. So can you write down in the chat, anyone? What exactly is A times A transpose or A square? What sort of entries does it have? Okay, to streamline the thing, diagonal entries equal to something and off diagonal or non-diagonal. Okay. Diagonal entries are the degrees, yes. So they are the degrees of this graph, which is not the graph we are interested in, but the super graph of that, right? So what exactly are those degrees? So the diagonal entries are indeed the number of ones in each row, right? So how many ones are there in each row? What exactly is that number? So in this, exactly, that's the answer. So this is the cardinality of PGS minus 2 comma Q, right? Because what are these vectors? So for every point X, it's a 1 here if that vector, that point Y belongs to X perp. So this is basically the characteristic vector of X perp, and X perp is just isomorphic to PGS minus 2 comma Q. So this is equal to, yeah, some constant, let's say delta, right? It's a constant. So all the diagonal entries of A square are a constant. What about the non-diagonal entries? Yeah, sure, common neighbors, indeed. So, and what's that number? So how many common neighbors do two vertices have in this bigger graph, right? In this A. Yeah. What is that number? Is it a constant? Right? That's the main question. Anyone in the chat? You can unmute yourself as well if you want. Yeah, exactly. So this is one lower dimension, Q, let's say mu. And the reason is as follows, because whenever you take X perp, it's a hyperplane. And whenever you have a distinct point and you take the perp of that, that's another hyperplane, and they meet in a one code, like in a codimension 2 subspace. That's the reason why this is also a constant. Okay, so now you can easily write down what the matrix is. So I hope it's easy to write down. So it's the, yeah, so we have mu times, yeah, you'll have to think. So you will have mu times J plus delta minus mu times I. Yeah, intersection of two hyperplanes. Yeah, exactly. So the intersection of two hyperplanes is always a constant, and one hyperplane also has constant size. So this looks very nice, right? Now we are in business. We know a really nice relation for A squared. So hopefully this will help us compute the eigenvalues of A. So that's the idea. Okay, so now claim delta is an eigenvalue of A with multiplicity 1. And the proof of this is an exercise. Standard spectral graph theory stuff. If you take the all one vector and you multiply this matrix with the all one vector, then you just sum up all the rows, right? So that's a constant which is equal to delta. So that's one vector, which is an eigenvector with this eigenvalue. And in fact, you can show it has multiplicity 1 by showing that this graph is connected. Even though it's not a simple graph, the same argument that we had earlier in the notes would work. Nice. So multiplicity 1, and yeah, the eigenspace of this delta is just the space spanned by all one vector. Okay, now let lambda be any other eigenvalue. Someone unmuted themselves. Do you have a question? No. Okay, so be an eigenvalue with eigenvector x, which is orthogonal to, I shouldn't use the same symbol, so maybe just orthogonal to the all one vector. Right, remember the real spectral theorem, you can decompose the vector space into these orthogonal, pairwise orthogonal eigenspaces. So let x be any other eigenvector, say lambda is the eigenvalue, then when you multiply this equation by x on both sides, this thing becomes 0. Right? So you have a square times x is equal to lambda square times x, which is equal to 0 plus delta minus mu times x. This implies that lambda is equal to either plus or minus square root of delta minus mu. So this matrix has really nice eigenvalues. Even though we don't have a strongly regular graph, we have these three distinct eigenvalues. The degree of the graph and plus of that and minus of that. Right? And this is exactly equal to the square root of q to the s minus 2. Okay, so now we have an eigenvalue of this matrix A. How do we use it? This is not an SRG because the loops, exactly. Thanks, Abby. So this is not a strongly regular graph because we have loops in this graph. Otherwise, if you have three distinct eigenvalues, I think, yeah, then I guess that, and a regular graph, that implies you have a strongly regular graph. Yeah. Nice. Okay, so this is not a strongly regular graph, but our graph is a subgraph, as an induced subgraph of this graph. So now we use something known as the interlacing theorem. So my handwriting is getting worse and worse. Okay, so this is interlacing lemma theorem, whatever, which says the following. So let A be a real symmetric matrix with eigenvalues lambda 1 greater than or equal to lambda 2 greater than or equal to so on lambda n, and let B be a principal submatrix. So a matrix that you get by removing certain rows and the corresponding columns with eigenvalues, let's say mu1 greater than or equal to mu2 mu m, then the following is true. Lambda I is always at least mu I lambda of n minus m plus I. So in particular, if m is equal to n minus 1, then you will get lambda 1 greater than or equal to mu 1 greater than or equal to lambda 2 greater than or equal to mu 2, and so on. So sort of they are interlacing each other, these eigenvalues. That's where the name interlacing comes from. Okay, so once you have that, then you are done. So this implies that the eigenvalues, this implies that, okay, so say D strictly greater than lambda 2 greater than or equal to so on lambda n are the eigenvalues of our graph G, then lambda 2 is less than or equal to the second eigenvalue here, which is square root of q to the s minus 2, and lambda n, so minus lambda n, is also less than or equal to square root of q to the s minus 2. Right? This implies that in absolute value, the second largest eigenvalue is what we want it to be. Cool. So we have proved what we wanted to, and I think I have overshot by a couple of minutes. So in the next half of the lectures, we will see a construction. Firstly, we will see a construction that works for all S. So we don't have this condition of S even. And then we will see the new construction that improves this bound. That is the construction that we came up with. Okay, so we have a 15-minute break. Let's meet after those 15 minutes then. Cool. Thank you. Okay, so welcome back. And now let's look at a construction with the same density, the same sort of parameters, but that works for all S. So we get an ND lambda graph, which is KS free, and we don't assume anything about S being even or odd. And this construction is in fact going to be much simpler. And so probably that could have been the first construction I showed you, but hopefully all of this complicated stuff we did will pay off later on. And so this construction is the one that appears in the paper of Alon and Gribelovich from 1997. And it's sort of the first thing you try once you have that main idea, right? So here they take Q to be even. We'll see why that's important. And they just write down the first example of a symmetric bilinear form that comes to your mind. Right? This is the so-called standard inner product in the real or complex space, a real space. Right? So just take this particular symmetric bilinear form. And Q is even, and S is any integer. And now just do the same thing as before. So our vertex set is the set of non-isotropic points, so the points which are not orthogonal to themselves. And the x comma y is an edge if these 2 points are orthogonal to each other. Okay. Because we are working over even characteristic, there's something fundamentally different about this construction compared to the previous one. And that follows from the following observation. So if x belongs to x perp, so if x is isotropic, then you have the following condition. Right? That's the, just plug in yi equal to xi previously, yeah, right? So these are all the isotropic points, solutions to these equations. But because we are working over an even characteristic 2 field, it implies that we have the following. Right? X going to x square is a field automorphism. But this implies that x is in the hyperplane. Defined by sum of xi equal to 0. Right, so the isotropic points, the points that we are going to remove from the projective space to get our graph, they form a hyperplane. It's not a quadric or a non-degenerate quadric anymore. Right, let's just draw this. We have a hyperplane. Inside our, let's say, the projective space. And so this is PG of S minus 1 comma Q, and this is the set of all isotropic points, a hyperplane. So this is isomorphic to PG S minus 2 comma Q. And our vertex set is here. So this is the set of vertices. Cool. And again, the fact that this graph is Ks plus 1 free is the same proof, right? So for here, not equal to 0, in fact, yeah, so not equal to 0. Yeah, it's the exact same proof. You just write down that if you have a bunch of non-isotropic vectors, which are pairwise orthogonal, then they must be linearly independent. And so you have an upper bound on the clique size based on the dimension. So this is the same proof as before. But what about the parameters of the graph? Well, now, in fact, this is exactly equal to q to the s minus 1. And yeah, this is exactly equal to q to the s minus 2. So what about the parameters? Well, n is just the number of points outside this hyperplane. So the number of points in this space minus the number of points in this space, which turns out to be exactly q to the s minus 1. What about the degree? Well, now if you take any, so now if you take anything here, any non-isotropic point x, then x perp is just another hyperplane. So x perp intersects this hyperplane, the hyperplane of, this is the hyperplane of all totally isotropic points. This is x perp. So they meet in a codimension 2 subspace. So the number of points in x perp which are outside the set of isotropic points has this cardinality, right? It is the number of points in PG s minus 2 comma q minus the number of points in PG s minus 3 comma q. So it's deregular, and we are not assuming anything on s. And lambda equal to q to the s minus 2 over 2 is the same proof. So proof is same as before. Nothing really changed, just that now we have a regular graph for all s. Cool. So this was the example that they gave explicitly in their paper. And then they said that for general fields, of course, you can do something similar. And the thing I presented is what happens when Q is odd. So for Q even, it's really a very simple construction. You don't even need to develop all the theory of polar spaces to actually see this, right? You can, this is self-contained, basically. You can write down the proof from first principle, from the definition of projective spaces. But why did I spend so much time then on a much more complicated construction that just worked for odd cliques? Well, because I want to get to the new construction, the best known construction so far, which actually improves this stuff, which improves these bounds. And to describe that, I need quadrics. I need this odd characteristic field, and I need the non-degenerate quadrics. And I really need all that finite geometry stuff. Otherwise, yeah, I don't think you can actually come up with that construction without knowing something about quadratic forms or finite geometry associated to them. So this is the new construction. Okay, let's go through this. Oh, no, wait, this is the old construction, sorry. So this is construction 1 again. And now, oh yeah, I see. So I wanted to describe the new construction starting from construction 1. Okay, so recall the first construction. We had a non-degenerate quadratic form, and we defined this graph on these non-singular points, and it turned out to be k s plus 1 free. Now, conceptually, what we did, what this new construction is about, is as follows. So we essentially partitioned the set of non-singular points into roughly equal halves. So they are the same size asymptotically, and we managed to show that at least one of the induced subgraphs on these partitions. So we managed to show, okay, this is the partition. And then we managed to show that this graph, so the subgraph induced on one of these halves, is in fact KS free. So So that's the rough description of our construction before I actually show you the definition. Right, so we took the same graph, we took half the number of vertices of this graph, and the regularity, in fact, reduced by half as well. But that's not a big deal, right? Asymptotically, this constant decrease in the number of vertices and d does not really matter too much. And the lambda stayed the same, but somehow, magically, we managed to destroy all the cliques of size s. So in this construction, you can actually show there are many, many cliques of size s. Any orthonormal basis, so to speak, will give you a clique of size s. And so you can't really just take any arbitrary partition, or you can't even take a random partition into two halves. It had to be something very specific, very algebraic that we did. Okay, and this is the construction. Okay, so let's go through this slowly. We start with an odd prime power. And now I define two subsets of the finite field FQ. So the set of squares, and here I'm only taking the non-zero squares. So all elements of the field for which there exists a non-zero b such that a is equal to b squared. And then these are the set of non-squares. Okay. And now I fix some non-square in this FQ. So Q is odd. We know that these squares and non-squares basically have the same size, Q minus 1 divided by 2. And I just pick some element, some fixed non-square eta. And now S is any integer. So I don't assume even, odd, or whatever. And I pick a very specific quadratic form. So a very specific equation. And it took us some time to actually come up with that. Earlier, our result was quite messy, but I don't want to present that. So I want to present the neat thing that showed up in the final published paper. So we pick this particular quadratic form where you have this non-square in front of x1, and then you just have 1 as a coefficient in all of them. So sum of xi square, right, this thing. And now, again, you just take beta, which is the symmetric bilinear form that this quadratic form polarizes to. And so you can just write it down as eta times x1, y1 plus sum of xi, yj, yi, I equal to 2s. So that's the symmetric bilinear form. You could just start with one of those two things, and that's fine. Okay, so it's basically the same symmetric bilinear form as before, but we twist it a bit. We add this eta in front of x1, y1. Okay, and now our vertex set is the set of all non-isotropic points. So qx non-zero, but we only take those points x for which q of x is a square. So morally, we take roughly half the points. At least that should be your intuition. Your intuition should be for that whenever q of x is non-zero, for half of the times it's a square and half of the times it's non-square. And that intuition is not that far away from the truth. In fact, yeah, they won't be equal always, but yeah, they're roughly equal. And again, the same graph, we just take orthogonality. Cool. So is the definition clear? What the graph is? Is that clear? Before we actually jump into proving any properties of this graph. If you have any question, just unmute yourself and ask.
Yeah, so just to be clear, for the vertices, you do not only require q of x to be a square, but also to be non-zero, right?
Yes, so it's a non-zero square, indeed. Yeah. That's how I'm defining my squares right now, just so that I don't have to repeat myself again and again, that we have a non-zero square. But very good point, we are not taking the singular points. We're only taking non-zero squares, right, this thing. What is the importance of eta, right? Yeah, that's the main thing. So if you don't take eta, then you run into some sort of a mess where you have to do a big case analysis that, yeah, if your Q is congruent to 1 or 3 mod 4 and your dimension is congruent to 1 or 3 mod 4, so you have these 4 cases, and depending on those cases, you have some result. So if the construction, the result that I'll state now, if you want to state it for general quadratic forms, you will have to do some case analysis. Right now, I just picked a very nice looking quadratic form to make my life simpler. And it will be clear why I need this eta. But keep that in mind. Yes, yeah, good question. Okay, yeah. More importantly, I think you should first ask me this question: is this well defined? Because one thing you should really think about is that these are projective points. So this condition should not change if you take a scalar multiple of x, if you take a non-zero scalar multiple of x. So that's important. And yes, it is well defined, because if you take q of lambda x, that just becomes lambda square q of x. So if q of x is a square multiplied by a non-zero square, you again get a square. So it's well defined. Okay, so on this page, I have 2 facts that I'm going to use, and I'm just going to hand wave my way out of this, because proving them requires some group theory, in fact. So maybe Emilio can prove this easily, but yes. Okay. First thing is this, yeah, the fact that the number of vertices is roughly half the number of non-zero, non-singular points. Should be easy enough to believe. You can show this by proving that qx equal to a has 1 plus little o of 1 q to the s minus 2 solutions. Oh wait, q to the s minus 1 maybe, because vector solutions for all a. Fix any a and you solve this equation, you'll get roughly the same number of solutions. And hence, if you are fixing half of the a's, then you get half the solutions, and then you divide by q or q minus 1, because yeah, we are looking at projective points. So that's a hand wavy argument. Ideally, this is not so obvious to prove. One guess for anyone would be to maybe prove that qx equal to square and qx is non-square, that maybe there is a bijection between the 2 sets. If you can prove that, then of course you'll get it, but that's not true, sadly. In fact, they could be of different size, but asymptotically, they always have the same size. So I hope you believe me here. I'm not going to prove this. Now, the second fact where I need Emilio is the following. This graph is in fact vertex transitive. So what does that mean? That means that there exists some automorphism of the underlying graph that maps any 2 pair of vertices. So whenever you have u not equal to v, there exists an automorphism of G such that sigma of u is v. And for this, you really need to look at the orthogonal groups, the underlying groups in all of these graphs, in this geometry that we are looking at. And once you know their structure, it's actually not so hard to prove. And in our paper, I think we give a sketch of this proof as well. But this would really require some theory. Okay, so these are the 2 facts I'll just take for granted, and I hope you believe me that they are true. And then just using these 2 things, I'm going to prove everything else. Okay, I hope you're happy with that. And this is really going to be crucial, because what this means, the way we are going to use this is as follows. Right? If GS is vertex transitive, then you can just focus on your favorite vertex. You can, whenever you want to prove some property of this graph, just fix a nice vertex which has some nice coordinates, and then look at the neighborhood of that vertex to derive the structure of the local structure of the graph at any arbitrary vertex. That's how we're going to use it. So this, yeah, lets you take, without loss of generality, like some very nice looking point. Okay, so if you believe me that these two things are true, then let's prove this. Okay, how do we prove that GS is KS free? Well, I'm going to use induction on S. And for that, I'll need this lemma that the neighbor for all vertices, the graph induced on the neighborhood of that vertex. So this is my notation. Yeah, just look at all the, this is my X, look at all the neighbors and look at the graph induced on these neighbors. This is, yeah. So this graph, I claim that this thing is isomorphic to G of S minus 1. And that's why, yeah, the eta and all will show up. So I claim that for any vertex, the neighborhood graph is just the same graph in one dimension lower. So the same definition, but for S minus 1. And now it suffices to prove that G of, yeah, you can prove that G1 is K1 free, which just means that G1 has no vertices. But just for the heck of it, just for fun, let's do a non-trivial case, because maybe then you learn something. So we'll start our induction at the next step because we want to make our life difficult. G2 is K2 free. And once you have these two, then you have the result by induction. Right? So G3, for example, is K3 free because if you look at the neighborhood, then the neighborhood, the graph induced on the neighborhood of any vertex has no edges. So it's triangle free then. So that's our approach. And how do we prove that? So let's say this is lemma 1, this is lemma 2. So proof 1. As I said, I'm going to use vertex transitivity, so I can just pick a nicely, like some nice vertex. I can just pick that. So let X be the following. Why did I pick that? Let's go back to the construction. Yeah. So if I pick the point where all the first xi's are 0 and only xs is equal to 1, then what happens in the neighborhood? Well, yeah, the neighborhood is just all the points where xs is equal to 0. Right? When you look at this orthogonality, all the points orthogonal to the 0, 0, 0, 1 vector is anything where the last coordinate is 0. Right? And so you just, this thing goes away, and then on this neighborhood, you basically have the same quadratic form. Right? You have the same quadratic form with one dimension lower in the orthogonal complement. So this implies that x perp is just all those y for which ys is equal to 0. And this implies that x perp is isomorphic to, or the graph induced on, yeah. And that's it, yeah. I'm going to write it. Is that clear? So really we use vertex transitivity. Otherwise it's not so, yeah, you get into messy things if you don't use vertex transitivity here. Right? Imagine if you just took an arbitrary vertex and you look at what the orthogonal space looks like. It's a mess, and then you want to show that the graph induced there is somehow isomorphic to the same graph. It's going to be very tricky. So this is where I use vertex transitivity. And then lemma 2 is again not so hard, I believe. Let's try. Okay. So let x be a point. So I want to show that the graph G2 has no edges. So I'll pick an arbitrary point of the graph and show that there is no neighbor there. So let's pick, I could have actually use vertex transitivity here as well, but let's prove the base case from first principles. So say we have A1, A2. Yeah, I'm going to remove this from the notation. Okay, so this is a point in PG1, comma Q, right? Then can you tell me what the unique point, which is orthogonal to X, is? So what is X perp? What is the unique point? So there's a unique point, right? In the PG1, comma Q, we have this orthogonality. So every point, if you take any point, its perp is just another point. So can you give me the coordinates of the orthogonal vector, let's say? Anyone in the chat? Let me write down the bilinear form again. Beta of x1, x2 is eta, x comma y is eta of x1, y1 plus x2, y2. Yeah, anyone wants to solve this? The good thing is we just want one solution, and then, yeah. Can you just guess some solution? Exactly. So y equal to a2 times minus eta a1. This is the unique point orthogonal to x. Okay, and now if q of x is a square, so q of x is exactly eta times a1 square plus a2 square is a square, then q of y, so y was this thing, so q of y is eta times a2 square plus eta squared a1 square. This is equal to eta times q of x. This is a non-square because we chose eta to be a non-square, right? So if you chose a vertex of your graph, then the unique point that is supposed to be adjacent to it will not be a vertex of the graph. It will be a non-isotropic or non-singular point, but it will evaluate, the q of y will evaluate to a non-square. Cool. Is that clear? Okay, it's just, yeah, to show how ridiculous this is, I could have started with g of 1, where q of x is just eta of x1 squared, and you immediately see that this graph has no vertices, right? Because if x1, yeah, if this is a squared, then this whole thing can never be a square, right? This is always a non-square. So I could have started with the simpler thing also. But another thing to note in this more complicated G2 is that note x going to x perp is a bijection between the following points, between all those x for which qx is a non-zero square and all those x for which qx is a non-square. So in fact, we gave a bijection. So in this two-dimensional or one-dimensional projective case, these two sets actually have the same cardinality, right? And since qx equal to 0 has at most two solutions, this implies that the vertex set has cardinality at most q plus 1 over 2 and at least q minus 1 over 2. So I'm also trying to convince you again that the first fact I said about the size actually makes sense. And in this two-dimensional case, you can just prove it easily. In higher dimension, it requires some more effort. If you can find an easy proof, that will be really nice. Cool. So once we have that, we have proved the following. Any questions so far? I'll take a pause now and then just let me know if you have any questions about this proof. Nope. Okay. Cool. And now the rest of the stuff is very easy because we already saw that n is, we already saw that this is true when I claimed it. And now because the neighborhood of each vertex is just the same graph, but with one dimension lower, the following is also true, right? And this follows from, again, just applying the interlacing theorem. Because again, we just take an induced subgraph. So you just take your adjacency matrix is again a principal submatrix. So you can bound the eigenvalues by the same bound. So n and d did not change much. Lambda did not change at all, but suddenly the graph is now ks free. So in conclusion, we have a ks free optimally pseudo random graph with d is equal to n to the 1 minus 1 over s minus 1. And d is off that out. So this implies f of s is in fact, we have a construction where f of s is s minus 1. And this improves the Gribelovich construction. So a very, very simple sort of observation, but of course it requires some effort to prove it and requires you to know a bit about quadratic forms and this finite geometry. And somehow come up with the square non-square trick. This is, cool. So that's it about the construction. Any questions? Any remarks? Any questions about the proof or construction or anything about this problem? Okay. Okay, if not, or does anyone have any question? Yosef, you just showed yourself. Okay, all good. So if not, then I don't think I should start another topic. We have only 5 minutes, so I would rather end early. Is the vertex
I have a quick question.
Okay,
so you mentioned in your paper that this is the same construction as Wilbrink when q equals 5.
Yeah, exactly. Yeah.
Okay, so I assume that, okay, because I'm reading Brouwer and draft of a book on spectral graph theory.
I see. Yeah.
And I think he describes these graphs for general Q as well.
Yeah. So for general Q, you can write down these 4 cases, and that's how we first described it. But it's just much simpler to present to someone with not that much background, like this nice construction. But it's the same thing. In fact, that's where it came from. So Ferdinand was working with Akihiro Munemasa on the strongly regular graph stuff, and that's where this whole idea in one of the strongly regular graph family, they noticed, oh, this does not, well, Ferdinand noticed that, oh, this does not have these cliques. Like the cliques that it's supposed to have, it does not have those cliques.
Yeah,
So
and he
maybe,
has that this kind of onion kind of thing, that the neighborhood is the previous graph and so on.
Yeah, exactly. And
So that
somehow, the clique number is one less than what you expect it to be. So
Mhm.
then he messaged me and then like, oh wow, yeah, okay, let's see.
Okay.
Let's try.
Very
it.
nice, very nice.
Cool, thanks. Yeah, and there's a question by Sahu. Is the vertex transitive part difficult? It's not that difficult. So if you look at our paper, which is there in the references, we have given a sketch there. So we explicitly talk about like, okay, here's a matrix, is an orthogonal matrix that maps any two vertices. But it requires some work. I think there also we assume some lemma already. So it's not self-contained. That's why we just call it a sketch. Yeah. Cool. Yeah. Any other questions or remarks? Okay, so I guess not. Then, yeah, before I end, let me just say that hopefully the same ideas or similar ideas will eventually lead to some improvement here. And hopefully that will lead to, then it will improve the bound on the off-diagonal Ramsey numbers. So in the next lecture, we are going to stop this off-diagonal Ramsey business, and we'll continue with multicolor diagonal Ramsey numbers, where recently a paper of Conlon and Ferber and then Wigderson building upon that, they have improved some of the known bounds exponentially. And again, the underlying argument is very finite geometric. So I'm going to explain that result, but more from the finite geometry side of it, hoping that that leads to some new ideas also. So that's it then. Thank you.